Alrighty, well, welcome back. We are continuing our way through chapter 18, and we're getting to one of the major points that come out of chapter 18. And so I mentioned this in the previous video. So if you take a look at all the examples we've been talking about and all the different reactions we've been doing, so far all we've been dealing with is some unreacted benzene, right? I can just scroll up here so you guys get an idea, right? So just some unreacted benzene and we add something to it, right? But the question is, so I guess essentially what I mean is we've been only dealing with mono-substituted benzene rings. So what happens as soon as we have something on the ring and then we're trying to add something else to it, right? So that's kind of what we're going to talk about here in this video. The first thing though is I have to give some terminology just so you and I can talk a little bit more efficiently about this. So if we've got a poorly drawn benzene ring, which we tend to have here, all right, and so let's define a point, right? We will just put a Q right there, right? Just as some point, it doesn't matter, we have something on the ring, okay? Then whatever else is going to come in. So let's say we're in the lab and we've got our compound there and we do some kind of electrophilic aromatic substitution, and so we want to add something to our ring. So there's, on paper, it looks like there's only 5 positions that we could add to our ring, right? So we have that, and that, right? We have those 5 open positions. Obviously, we can't add anything to this carbon here, right? Because that would create a carbon with 5 bonds to it. Yeah, 5 bonds to it, and that's just not going to happen, right? So we only have 5 places that we could add to that ring. But in reality, there's really only 3 places we could add to the ring, okay? So I'm going to come in, right? We have these positions here in green, okay? We have these positions here in red. And then we'll do black, sounds good. Okay. So do you guys see how the green positions, the red positions, and the green are both the same, right? It doesn't matter whether it's to the left or to the right, okay? And the red are the same, doesn't matter whether it's to the left or to the right of Q, and the black is unique. So really there's only 3 unique positions that we can add something else to this ring. So that's good, we're down from 5 to 3, okay? But from there, we're also going to narrow it down to really only 2, depending on what Q is, right? So that's what we're really going to talk about. We're going to talk about how Q affects whether things go to the green, red, or the black positions, okay? And what we're going to find is green and black tend to be, when we add something to green or black, those come together, right, as a set, and then red is kind of a separate case, right? So we're kind of narrowing it down to 2-ish positions that get added to it. But let's get some terminology with this. If we are in the green position, this is called ortho, right? In red, this would be called meta. In black, it would be para, okay? So those are the ortho, the meta, and the para positions. So what I'm going to be talking about here in the video and for the upcoming rest of the aromatic chapter, we're going to be talking about Ortho-Para directors or meta directors, okay? And so when I talk about ortho, meta, or para directors, we're just saying, how does Q affect where the incoming group goes? That's all it is, okay? So I have one thing, and I'm going to add 2, right, okay? And so we can even expand out from there and say, now I have 2 things, where does a 3rd one go? Where does a 4th one go? Where does a 5th one go, right? So we can just continue this on perpetually is what it is, right? So, but we'll build it up systematically. We'll start with one thing, and then we'll see where that goes, okay? So let us, I think this part of the chapter is always easiest just to, look at examples and kind of see how things go, and it gives us a good chance to, well, let me do a different color. And it gives us a good chance to kind of, I don't know, do a little bit of practice, I guess, along the way. Okay. So there's an example. We got our buddy T-butyl benzene here, tert-butyl benzene, and we are going to be adding this stuff to it. So pause right here, right? and see if you guys can come up with what the answer would be. Now, look, I know I talked about a little bit, talked with us a little bit about that, I believe in the last video also. You guys have all the answers already, okay? All the information that you guys need to be successful in OChem 2, you guys already have. This, we taught you this in OChem 1. So really, I could just say this and say, okay, why don't you guys go through and, you know, see if you can come up with the answer. And you should be able to, okay? Because we know what happens when we mix these two together, okay? That we talked about in one of the previous videos. Oh, okay, we got nitric acid, we got sulfuric acid. We're going to end up generating a good electrophile, okay? That electrophile is then going to be attacked by the ring, which generates a carbocation on the ring. And what is the name of the game with any carbocation? Well, the name of the game with any carbocation is stabilize it, right? How do we stabilize carbocations? Well, we have inductive effects, we have hyperconjugation, we have the resonance structures, we have other methods that we can put together to stabilize a positive charge, okay? And so what I could say is take a look at this ring, add our electrophile to it, and what do you start to notice about how the Q group, the T-butyl in this case, right? How the T-butyl group there, the Q group, would affect the stability of that carbocation. That's really what I'm asking, okay? Do you guys catch all that? Okay, let me go back and, too long didn't read. Okay, so what I'm asking is, how does the incoming electrophile get affected by what's already on the ring? And the way you answer that is by drawing through the mechanism. Got it? Now I told you guys that there's really only 3 options, ortho, meta, and para. And so when I ask you guys, see if you can figure out what the answer is, what I'm saying is, go through and draw the mechanism if I add something at all 3 of those positions. And see what would be different, okay? And there's gonna be an obvious difference between one of those and the other. That's all I'm asking you guys to do, okay? Did you guys catch all that? So pause, do that, draw this mechanism 3 different times for adding something at the ortho, meta, or the para position. And see if you can say, one of these, or one of these looks different than the other ones do, okay? So that's what we're gonna do here, right? We're gonna start by adding things at the ortho position, okay? So I'm going to, for the sake of, I guess, time, I'm going to skip making the electrophile, okay? Because I'll scroll up here for just a second. No, it wasn't all that long ago. Where is it? Maybe it was all that long ago. Okay. So here is where I talked about how to generate the electrophile for my nitration reactions. This is in one of the previous videos. So I'm going to just start with this right here, okay? So if you guys want to pause and look at this, or I should have my notes uploaded for you guys sometime soon, I hope. As soon as there's a little bit of a hiccup technologically here, but hopefully I'll get that resolved for you guys. But anyway, take a look, and I'm just going to pull this in, okay? All right, let's go back. Let's zoom in way too much. That sounds good too, all right. All right, so starting with my NO2, let's see, green for ortho, all right. So N nitrosyl group here, right? So let's reach this out, grab that. So we generated our electrophile. We are now adding that electrophile to the ring, okay? We'll come back in just a minute and finish it up, right? What do we have? Well, so here is our intermediate. This is our rate determining step, right? Generating a carbocation is almost exclusively the rate determining step. I really, off the top of my head, I can't think of an example where it isn't, although maybe, I'm sure somewhere there might be one case where it isn't. But at least for if we're dealing with undergraduate level OChem, almost 100% of the time the generation of the carbocation is going to be your rate determining step. So if we can lower, right, if we can stabilize that rate determining step, lower the energy, lower the hill, lower the barrier, whatever you want to say, then, you know, we can make this reaction proceed faster, right? Anyway, so there's our positive charge. We generate a carbocation, we stop, we think, we look, we see how we can stabilize that charge, okay? Now, let's stabilize this by doing some resonance structures. Oops, got a little bit ahead of myself there. Okay, there's that. We moved this over here. I'm just going to abbreviate that as NO2 if you will allow me. All right. Have this over here now. Good. Let's see, everything should be in green. So we got green, positive charge there, NO2 there. Okay. And that's it for the resonance structures we can draw, right? We don't have another pi bond here, right? So we could go back, we could draw a set of arrows to go back to where we started though, right? So those are all the resonance structures that we can draw. Great. Let's pause with this. All right, now we'll go on to, I believe we used red. Okay, so now let's do the exact same thing for when we add something to the meta position. And hopefully if my directions for you guys earlier wasn't clear enough, maybe now you get the idea of what I wanted you guys to do. So again, if you want to pause here and fill in for the meta and the para position, then, oops, I did forget an arrow up here. There we go. Now I've got 100%, all right. This, we added that NO2 here, and now we have that there, okay? Play the same game. This is blue, NO2 here, right? So this is red, that's there, move it one more time. Okay. We pause, we sit back, we admire our fancy drawing and go, wow. Okay? Well, what do we notice is the same and what do we notice is different so far? Well, nothing's different at the beginning. Ring reaches out, grabs the electrophile, right? We end up generating a positive charge. We can draw a set of 3 resonance structures. Okay. Well, there's no obvious difference maybe, or is there, right? So let's say I think black was the last one used, right? Cool. So let's do the exact same thing one more time. Start out with my benzene ring, and I shouldn't do that. I gotta show the arrows, right? Okay. This. I'm trying to match up the positioning of the benzene rings all with each other as much as I can. But if you guys have made it with me this far, you know that sometimes my artistry is not the best, and that's okay. Not the Bob Ross of chemistry, right? So, all right. This is in blue. So we got black, 2 positive charge there. Okay. So let me see if I can zoom out here. Hopefully, I hope that kind of shows up on the screen there so you guys can see that all at once. I wish I had somebody working the camera here so we could zoom in on things, but hopefully this is still kind of showing up for you guys. Here's the point, okay? the point is we can draw 3 resonance structures with all of these potential mechanisms. So we can't immediately go through and discount or say that one of these is better than the other simply based off of how many resonance structures, right? Because there was this, remember there was this idea that kind of came out of OChem 1 that said the more resonance structures you can draw to spread out a charge, the more stable that becomes, and thus, you know, the more favorable that formation of that carbocation becomes, right? I'm not saying it's easy to do, it's just easier to do, right? So 3 resonance structures, 3 resonance structures, 3 resonance structures. So it's not the amount of resonance structures that makes a difference. The difference comes from where that positive charge is. If you take a look at the green and the black, so the ortho and the para mechanisms, the difference comes from here, okay? So I'm going to zoom in on this so you guys can kind of catch what I'm saying there, right? So I'm going to box, let's see, what color do I want to use? Yellow, so I don't get confused here, right? So I'm looking at this resonance structure, right? And I'm looking at this resonance structure right here. So I'm just going to zoom in on one of those. Okay. This is the resonance structure that makes the difference. It doesn't necessarily matter yet where the NO2 is, okay? It matters where the positive charge is. So in those resonance structures that I boxed that are yellow, the positive charge is sitting on the carbon where that T-butyl group is. Got it? So let's think here for just a second, right? If you go back again to OChem 1, my goodness, it's almost like that's a really important class, right? If you go back to the principles that we learned in OChem 1, we talked about how we can stabilize carbocations. And one of the methods was, you know, by having a tertiary carbon, right? Those are more stable carbocations than secondary, okay? Why? Why is a tertiary carbocation more stable than a secondary? And this is a genuine question, right? So again, I'm going to ask you guys to pause and see, can you actually answer that? I know you guys know that, right? Let me pull out my, my flashcards here. Yep, tertiary more stable, right? Why is that? Okay, why is a tertiary more stable than a secondary? Okay, and the answer, I'll give a quick pause here for drama, right? The answer is because how do you stabilize something that's positive? Well, I've mentioned this before, right? To stabilize a carbocation, you have to give it electrons, okay? I'm not talking about just pouring a bucket of electrons in there, right? I'm talking about by what is around it, we can donate electrons to it. What is different about a tertiary versus secondary carbocation? Well, it's how many bonds are around it. Okay, we'll take a look. We got bond, 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 right? What are bonds made out of? I hear the answer, right? It's electrons. So if you have more bonds around it, right, that means you have more electrons around something, so we can, that positive charge is going to attract those electrons to it and help stabilize it, right? Inductive effects, a through bond effect, right? So that's kind of the rationale here. But the point being this, so let's take that principle of giving things more electrons to stabilize it and take a look at alkyl groups. Now we know from our study of carbocations in the first semester, right, that tertiary is more stable than secondary than primary. So if we can generate a positive charge on a tertiary carbon, then that's going to be more stable. But the point being this, what we were really saying is that alkyl groups are electron donating, okay, and they are. And that principle is going to work exactly the same here. When you see, here's the kicker, right, so if you guys are tabbed over to something else, come on back, right? When you see an alkyl group bound to an aromatic ring, we consider them electron donating, okay? So they're basically pumping electrons into that pi cloud, okay? And that causes two things to happen. And oftentimes these two things are conflated, okay? So here's what it is. When we have an electron donating group, okay, we tend to call the ring activated, okay? And electron donors are Ortho-Para directors. You guys with me on that one? So if we have an alkyl group, it's going to be donating into the ring, which activates the ring. We'll talk about that in just a second, right? So the ring is activated, and it is an Ortho-Para director. Why? Why are these electron donating groups ortho-para directors? Well, because if I add something into the ortho position and into the para position, I can put that positive charge onto the group that is donating electrons, aka I can make a more stable carbocation. That's it. So out of all this, I think if I'm looking at the time properly here, I think I'm about 20 minutes in, and I could have just said, stabilize the cation. And you guys would have said, okay, yeah, I'm used to doing that. Yeah, that's great. That's all it really comes down to, okay? So you go through, you draw a mechanism, you look at the positive charges and go, which one's the most stable? Aha, right? This positive charge is next to an electron donating group, right? So that's going to be more stable than in the red where we don't have that, right? If I add things in the meta position, right, we never end up putting a positive charge on that electron donating group. So that's going to be less stable, okay? So ortho and para are going to be the preferred positions of adding a group when you have electron donors on the ring. Okay, you guys with me on that one? That's the big kicker to that. All right, but wait, right? There's more. So that being said, right? That being said, so let's go back and simplify for just a second. So here's what we started out with. We'll do it in black. HNO3, H2SO4, right? So if we come back and we get this idea, right, here's an exam question, not really, the exam questions aren't going to be this easy, they're going to be super hard, just the hardest questions ever, okay? So we're going to take this aromatic ring, we want to nitrate it, right? And so we might just say, oh, okay, it's an alkyl group. That means the ring is activated and they're an activator, thus it's going to be an ortho-para director. So we have two ortho positions, we have one para position. So by statistics, we should expect to see twice as much ortho product as we do para product. You guys with me on that? If we just look at this as a whole, we have 33% of the time, right? Three positions, everything being equal, two of them being the same, so to speak. Then what we would expect to see is this, right? And we, just in theory, we would expect to see that 66% of the time. Whoops, I meant to do this in blue. All right, so the ortho in green there, and we would expect to see this about 33% of the time. Does that make sense? You guys following along, right? These two positions are equal, and both of those are 33%, blah, 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 right? So, in reality, that's not the case, right? This would be the case if electronics would be the only defining or driving force behind this. So here, I'm going to give away my big secret, okay? The reason why I am a chemist is because I can sound really smart by only talking about two things. And those two things are electronics or sterics, okay? That's really it. Especially when you guys get to inorganic chemistry. If you guys are ever stuck and oh geez, what is it? Just start with either electronics or sterics. And usually you will be right, okay? And then, just spread the secret around, right? But here's what I mean. Right? When we're talking about why something happens or explain this phenomenon or something like that, electronics just refers to where are the electrons, right? And that's what we did with drawing our mechanism and drawing our resonance structures. That's just talking about where the electrons are. You guys will learn more about this in depth when you get to physical chemistry, when you talk about molecular orbitals, and inorganic, where you talk about symmetry adapted linear combinations and salx and all this other kind of stuff, right? But don't worry, that misery will come later, okay? For the moment, when we talk about electronics, it's just basically think about what the mechanism is and the resonance structures and all that kind of stuff that goes with it, all right? So that's electronics. Sterics is basically social distancing for atoms, okay? Ha ha ha, topical humor. Okay, so what I mean with sterics is, so think about this, right? When you go to the movie theater, right? And maybe it's, maybe not opening weekend, but not too far away from that, right? When you go in there, the room might be kind of crowded, and what do? You look for a set of seats that's kind of away from everybody else, right? So atoms behave the same way. They kind of look to stay away from other atoms because, right, if you take a look at it, that T-butyl group, it is actually a huge group. We don't draw it quite to scale, right? But there's a lot of atoms that are involved in a T-butyl group, so it takes up a huge amount of space. It physically takes up a lot of space, right? And so in reality, the para position is going to be preferred far more often than the ortho position is, especially when you have bulky groups on the ring already. And for T-butyl, it's hard to get things that are more bulky than a T-butyl group. So almost exclusively, this is going to be, in reality, it's going to be more something like, actually, do we have an example of this? They might have actually talked about this exactly in the book. I should have looked that up. I guess not, but that's okay. I'll put some numbers on here just for emphasis sake. So in reality, this is probably going to be something like 90% of the time and maybe 10% of the time, although I might be even off. It might be closer to like 99 to 1, right? But because of sterics, we prefer the para position. Because of electronics, we prefer both the ortho or the para. Got it? You guys with me on that one? So electronics tells us about where it's going to add either ortho or para, and looking at the sterics of what's on the ring is going to say that usually para is preferred. Now obviously, and there's the, I'm looking at page 805, so 805, if we went back and we could do this example with not a T-butyl group, but a methyl. So if we have just a methyl group there, less sterics, and we actually do start to see the preference for the ortho position come in, right? Because statistically, right, it's easier to, right, there's more opportunity to add it in ortho, right? So that might be the idea to think about with that. But in general, right, if we do want to make another flashcard and say, what happens most of the time? If you have an activator, it's going to be Ortho-Para director, and typically it's going to add, or it's going to prefer to add to the para position. Got it? That's the kind of name of the game, okay? All right, so let's talk a little bit about what actually makes a group an activator or a deactivator. So let's give the quintessential examples here. Maybe not quintessential, but you know, just the most common or very common, and get the point across. Okay, so we got these two examples here. We have, this is anisole, right? It's just the common name for that. And this is benzaldehyde, okay? Here's my question. One of these rings is going to be activated. One of these rings is going to be deactivated, okay? One is going to be activated, one's going to be deactivated. What does it mean to be activated? Okay, well, if I have an activated ring, that means my ring has more electron density in it. It's going to be more negative, okay? If I am deactivated, that means I'm going to have less electrons in my ring, so I'm going to be more positive feeling, okay? You guys with me on that? So pause here, see if you guys can figure out which ring is activated, which is deactivated, and why. Okay, so which ring is activated, which one's deactivated, and why is that? All right. Okay, so here's the 30-second, well, maybe even less than 30 seconds. Right, here's the 5-second answer. Okay, there it is. Got it? Okay, thank you for your time. We'll see you in the next video. Okay, the point is this. Okay, or let me back up for a second. If we want to put electrons into an aromatic ring, if we want to activate the ring, then we better darn well put our electrons right next to the ring. And I'm talking about the atom that is directly bound to the ring. The atom that is directly bound to the ring needs to have lone pairs on it for the ring to be activated. Got it? So the atom directly bound to the ring needs to have lone pairs on it for it to be activated. Then you don't have to memorize the list of stuff that they put into the book here. Where is it? I just saw it on page 812. Page 812 for activators and deactivators. Oops, sorry, let me edit this better page for you guys. They kind of put everything together. So page 814, right? So they have a nice table there. If you guys are like me, I've got limited brain space, I've got too much useless information right here already, and I don't want to sit here and memorize like, oh, okay, you know, what is a strong activator and a moderate, I don't have time to memorize all that stuff. I got better things to do, okay? So what I do instead is understand why something is an activator and something is a deactivator. And it all comes down to this. I need lone pairs so that I can draw resonance structures to push a negative charge onto the ring. That's it, okay? Here's what I mean, okay? I can draw a resonance structure wherein I can take a lone pair, right, from my group that's bound to the ring, right, and push a negative directly onto the ring. Notice where this negative is. It is right next door to the group that's already on there. So this is an ortho substituted negative charge. Do you guys catch where we're about to go with this? If this is more negative, and we're doing electrophilic aromatic substitution, why do we call these activated rings? Well, we couldn't put a negative charge where we're going to add this stuff, right? If something is feeling more negative, it's definitely going to go after stuff that's more positive. Did you guys catch that, right? Not only are we activating this ring, if you take a look at where the negative can end up, and please go through and draw the resonance structures, right? We put the negative charge here, here, and here, right? That's why we can explain that the Ortho-Para Directors, and we can explain why it's activated, okay? You guys with me on that one, right? So really what I'm saying, how do we know if this is an activator? Look for lone pairs, push a negative charge into the ring. You can't do that here, okay? In fact, it's going to be opposite, okay? Because, right, there's no way to get these lone pairs into that ring. The opposite happens, in fact. Watch. I think I got to zoom out just a bit here. Here, blue, and then this is going to be positive charge, negative here, and I put that there, right? So now we actually have a positive charge on the ring. If you are positive, are you going to go after an electrophile? No, you are not, right? So we have deactivated the ring, right? We've made it feel more positive. It's going to be harder for it to go after the next thing that's coming in here, okay? So how do we identify deactivators? There's two ways, okay? There's two common traits. The atom that is directly bound to the ring here is a carbonyl carbon. How do carbonyl carbons normally feel? Well, they're feeling partially positive, okay? So if you have a partially positive or full positive atom that's sitting directly bound to the ring, you're going to be deactivating the ring. The other thing to look for is, do you have a conjugated set of pi bonds with the ring? Do you guys remember what it means to be conjugated? This is what we talked about in chapter 15, I believe, chapter 15 or 16, something like that, right? So go back to, now I'm curious. Yeah, sorry, chapter 16 is where we talk about conjugated pi systems, right? So pi bonds that are next door to each other. So this is a conjugated pi bond, and we can end up generating a resonance structure like this, okay? So if you take a look on page 814, right, look at all the pi bonds that we have bound to the ring in all of those examples. And what they do is we can then draw resonance structures where we put a positive charge in the ring. That's it, okay? That's it. So what are you doing? What's the quick summary here? Let's wrap this up real quick. So when you start to add things to an aromatic ring, okay, when you start to make a di-substituted or tri-substituted aromatic ring, you need to assess whether what's already on the ring is an activator or a deactivator. An activator is going to have lone pairs on the atom directly bound to the ring. A deactivator is going to have a positive charge on the atom directly bound to the ring and look for pi bonds. If you're an activator, you are activating the reaction. It's going to go faster, okay? The reaction, electrophilic aromatic substitution, is going to go faster with an activator on the ring. Deactivators slow down the reaction to the point where they might not even happen. That's where the word activating and deactivating comes from, right? Makes it faster, makes it slower. Sometimes they're spontaneous to speak, and sometimes they don't even happen at all. If you are an activator, then you're going to be ortho and para directing. Para is going to be preferred based off of sterics in 95% of the cases, right? Deactivators are going to put things in the meta position. Can you guys figure out why? Why, if I am a deactivator and I do undergo a reaction, would I prefer to put things in the meta position? Activators, ortho-para, deactivators, meta position. Why is that? What am I asking you guys to do? I'm asking you guys to draw the mechanism for something, okay? So I'll leave you with this, and we will pick up the answer in the next video. But here's what I'm asking you guys to do, right? Let's say we have our buddy benzaldehyde, and we try and do a nitration with it. And I'm saying explain why this, oops, not HNO3. Explain why the meta, right? 1, 2, 3, right? Why the meta is the preferred product for deactivators. And the answer is draw the resonance structures, okay? Okay, so that's good for there, I think. We'll give some time for that to kind of settle and marinate, so to speak, and then we will be back with the next video and we will continue on in this chapter.